Hey everyone, my name is Lyndon Hillenbrand, coming to you from Cloudera HQ, and we're going to talk about MapReduce and HDFS. So today we're going to talk about what is MapReduce, why did we choose MapReduce, the framework and the architecture around it. Then we'll talk about HDFS, which is the Hadoop distributed file system, how it breaks files up into chunks, how it operates, and then we'll talk about feature plans and what's coming along in CDH3 and CDH4. So how is MapReduce structured? Well, MapReduce is a functional programming model that meets distributed computing. It's a batch data processing system. It is not real-time, and it factors out many reliability concerns from application logic, such as hyperthreading, such as multitask procedures, such as operating on a distributed cluster. MapReduce provides automatic parallelization and distribution, fault tolerance, status and monitoring tools, and a clean abstraction for programmers, away from all the nitty-gritty details on how it actually distributes itself across the cluster. So what's a programming model? Well, MapReduce is a framework using two functions, map and reduce. They both take key value pairs that are passed to each other throughout the framework. So it borrows from functional programming. And the two interfaces we just talked about, you see map, where you have a key and a value as input, and then the intermediate, which is the output of the map, is also a key value in list format. And then you have the reduce, which takes that intermediate key, intermediate value list, and outputs a single key and value pair. So let's start with the map. Records from the data source are fed in the map function as key value pairs. And the map produces one or more intermediate values along with an output key from the input. So if you look at the diagram on the bottom, we have an example where there's two text files. You have a map task, which splits the data input into multiple key and value pairs. Then you have the middle section, which is a shuffle phase that we'll talk about. Then you have the intermediate data coming into the reduce task, and a single output, which is a key value pair. So let's take a look at some examples. I think that's the best way to take a look at how MapReduce operates. This is a simple uppercase function leveraging the MapReduce framework. So let's let map and key value emit a two-upper function for the key value pair. If we pass it foo_bar, it's going to output foo and bar. Very simple. And the mapper can operate alone. There's no reason to have a reducer unless you're doing some sort of reduce function or aggregation. So if you look at the explode mapper, all it's going to do is take the key and the value and map the key to the value for each value in the actual value variable. So the explode function uses a map method where the data set is split into key value pairs. And we take A and cats. A is going to map to C, A, T, and S respectively. So if we look at the filter mapper, all it's going to do is filter something where if it is prime, it'll emit the key value. So now you can understand the MapReduce framework can be used as a standalone map method for data analysis. Let's look at the reduce phase. The primary goal of the reduce phase is to do aggregations or your more complicated functions once everything's been mapped from the map phase. So all the intermediate values that come out of the output of the map phase are given an output key and are combined together into a list. The reducer combines these intermediate values into one or more final values with the same output key. So let's take a look at the sum reducer. So we can let the reducer equal a key and value pair, sum equals 0, and then for each integer v in values, we're going to add that to the sum. So you can see the examples of A and B below. So let's talk about why MapReduce is so beneficial and where it gets its power. Well, it has data locality. So the data is passed to each of the data nodes within your Hadoop cluster, and MapReduce packages your MapReduce functions as a jar file and sends that to each node. The jar file operates locally on that slice of input on the data node. So every function that you write for map and reduce is operated X number of times on each on each of the X data nodes that you have in your cluster. So for example, if you have 50 data nodes, that jar will be run 50 times. So MapReduce, how does the actual execution work? So in this depiction, you have your data nodes, and you have your data inputs. Well, there's a mapping process, and then that maps to several data nodes. It'll run the reduce phase, and the reducers will run on their data nodes respectively. So parallelism, that's the key to MapReduce. So map functions run in parallel, creating different intermediate values for different input sets. As we talked about, everything is run locally on the data node. That's where it gets its power. The reduce function is also run in parallel, each working on a different output key. All values are processed independently, and you can already see a bottleneck is where the reduce phase can't start until the map phase is completely finished. Let's take a look at an example. Word count. You can see the map and reduce function defined here, where you have an input key, an input value, and an output key and an output value. This is a perfect example of the MapReduce model running the word count process. You take a set of input, might be deer, river, cat, bear, then you have a final result. And the splitting, mapping, shuffling, and reducing are the exact phases it goes through to operate on that data set. So there's also a combining phase, which is where you can run almost a mini reduce phase in between the map and reduce phase. This is used to save bandwidth before sending full data to the reducer, and the reducer can use a combiner if a commutative or associative function is needed. For example, sum reducer. So what are some MapReduce conclusions? MapReduce has proven to be a very useful abstraction in many areas. Greatly simplifies large-scale computations. It's a functional programming paradigm that can be applied to large-scale applications, and you focus on the real problem, rather dealing with the messy details of how it actually distributes to the nodes and operates locally. So just keep in mind that writing MapReduce is a completely different way of thinking. You're writing your map function, which is splitting your data. Then you're writing your reduce, which is basically your aggregate function. So let's talk about HDFS. So MapReduce in conjunction with HDFS forms the Hadoop core. So HDFS is a Hadoop distributed file system, and it's based on Google's original distributed file system. It's redundant storage of massive amounts of data on cheap and unreliable computers. So if you could take a large HPC cluster from any vendor and match that to 1,000 computers that are unreliable with this system on it, the unreliable cluster will actually stand its ground against the APC system and be much cheaper. So that's the reason Google started thinking, if I could actually map these computers to work together, and upon failure of one of the nodes, I can just replace it with another, it's not a problem. Performance is not affected, other than some fault tolerance that has to be handled. So there's different workload and design priorities that we're going to talk about, and how to handle much bigger dataset files and other file systems. So there's a lot of complexity under the covers and assumptions that we have to make about HDFS. There's going to be high component failure rates when you're using cheap computers. Inexpensive commodity components fail all the time. But if you can have the system fail linearly rather than fail all at once, you're already on the winning side. So to be modest, we have a huge number of files, right? Let's say a few million. Each is 100 megabytes or larger. Typically, there's multiple multi-gigabyte files. The file system itself is a write once, mostly read. It has a large streaming reach, and it has high sustained throughput favored over low latency requests. This is where the key batch processing really comes in. There's some specific design axioms that Hadoop runs on. Files are stored as blocks. Those blocks, some can be commonly referred to as chunks. By default, they're split into 64 megabytes. Actually, we recommend now about 128 megabyte chunks as the RAM increases on each of the data nodes as we're going forward on commodity machines. There's reliability through replication. So we're starting to talk about commodity hardware failing? Well, there's a replication factor of 3 plus across your entire cluster, and that can be set in your HDFS config. So if you want your replication factor to be 1, where if a node fails, you lose the files, that might be fine. It might have to be 9 or 10 if you really want to secure your data, but 3 seems to be a safe and secure manner. There's a single master, which is referred to as a name node, which coordinates access and metadata. It's your centralized management system, basically. The name node stores your metadata file in memory. So there's no data caching here. There's little benefit due to large data sets because of the streaming reads. There's a familiar interface and customizable API that you can use. Let's take a look at how the blocks are actually distributed and stored. So you can see here that there's a client computer, which will submit files from the local file system to HDFS, and the name node will know the location of where those files are being stored and replicated to on each of the data nodes. There's actually a heartbeat communication between the data nodes and the name node to make sure it understands that they're up and available and where those actual file locations are residing on the data nodes. So block allocation in HDFS is basically completely random. As you can see in this depiction, the name node stores the metadata only. So it knows about the file system, knows what user you are and where you're operating on, and the data nodes basically don't know any of that. They just store files. So let's talk about the GFS architecture. Basically, it runs as a master, and then you have several chunk servers. And this is exactly how HDFS is laid out. So the metadata. The metadata is extremely important. There's a single name node that stores all of your metadata. This includes file names, locations of each file in the data nodes. They're maintained entirely in RAM for fast lookup. So you do need a lot of RAM on your name node, especially if you're having a large number of files sitting on your data nodes. Data nodes store the opaque file contents in block objects. Basically, if you have a 1 gigabyte file, that 1 gigabyte file will be split into chunks, stored on different machines across the cluster, and replicated 3 times. So it's very complex, but all of these complexities are hidden under the covers to the actual user. So name node failure resistance. So you can already imagine that if your name node fails, you lose location of all of your data blocks on your cluster, essentially losing access to most of your data. Well, the namespace image and the edit logs can be stored to disk. These are merged by something called the secondary name node daemon that you can run on a separate data node. Now, it's not considered a hot failover or even high availability. For example, you might take a snapshot every 10 minutes of your name node image file. In that case, if your Hadoop cluster goes down, you lose about the last 10 minutes of data. Currently in CDH4, we're working on a high availability name node for the next release. So in summary, HDFS supports large-scale data processing workloads on commodity hardware. It's designed to tolerate frequent component failures, optimized for very large files. Not only that, but a large number of files. You might have a 50, 100, 1,000 node cluster. We've seen several organizations that operate 4,000 node clusters. The file system interface is customized for the job, but still remains familiarity for developers. And simple solutions can work. There can be a single master, you can have a failover, you can run the secondary name node. It's really all up to you. So reliability stores several terabytes in individual clusters. Data sizes range anywhere from a petabyte, 10 petabytes, 100 petabytes. So that's MapReduce and HDFS and an introduction to it. So thank you very much. If you have any questions, visit cloudera.com. You can find us on Twitter or Facebook, or give us a shout. Thank you.